Welcome to this module. Here we are going to discuss Cauchy's convergence criterion. The last theorem on the previous module stated that in R, the set of real numbers, every Cauchy sequence is convergent. This can be used to check the convergence of a sequence. Thus, we have the Cauchy convergence criterion as follows: Cauchy's convergence criterion a sequence of real numbers is convergent if and only if it is a Cauchy sequence. It is a Cauchy sequence. Thus, being a Cauchy sequence is sufficient to be a convergent sequence. Using this criterion, we will prove some interesting results in this last module of this unit. Take this example. Let xn be, the sequence xn be defined as x1 equal to 1, x2 equal to 2, and for the rest xn will be half of xn minus 2 plus xn minus 1, that is for n greater than 2. Now, first we show that all the xn's are lying between 2 and 1. Right. This can be done using the method of induction. We use method of induction for this. Right. x1 and x2 satisfy our assertion, that is, they are lying between 1 and 2. Let for k less than equal to n, all the xk's are lying between 1 and 2. Now, take k to be n plus 1, and we want to show that one less than x n plus 1 less than equal to 2 also. This is what we want to show by the induction hypothesis. Thus, x of n plus 1 by the definition of the sequence is half of x n minus 1 plus x of n. By simplifying, 2 x n plus 1 would be x of n minus 1 plus x n. By induction hypothesis, x n minus 1 is lying between 1 and 2, and similarly x n also is lying between 2 and 1. Adding these two inequalities, we will get two is less than x n minus 1 plus x n is less than equal to 4. And therefore, 1 is half. If I multiply it by half, this is going to be x of n minus 1 plus x n less than equal to 2, and this is the value x n plus 1. Therefore, 1 is less than equal to x n plus 1 less than equal to 2. This is our assertion. For that assertion, first we have to show that x n minus x of n plus 1 is equal to 1 by 2 to the power n, and then definitely it is less than equal to 1 by 2 to the power n minus 1. It is strictly less than 1 by 2 to the power n minus 1. But since this is done using method of induction, and it is easy to show that, therefore, this is omitted here. For m greater than n, by triangular inequality, we have x n minus x m, which can be written as x n minus x n plus 1 plus x n plus 1 minus x n plus 2 plus so and so forth, and the last term would be x of m minus 1 minus x of m. By this property, I can at once write here less than equal to 1 by 2 to the power n minus 1, 1 by 2 to the power n, so and so forth. Ultimately, it will be 1 by 2 to the power m minus 2. Take 1 by 2 to the power n minus 1 common, we have 1 plus half plus and so forth. The last term will be this time 2 to the power m minus n minus, and this is definitely less than 1 by 2 to the power n minus 2. This part is a GP, thus we sum up the GP and we can always find out an inequality of this type. Thus, given epsilon greater than 0, choose n, a natural number, such that 1 by 2 to the power n less than epsilon by 4, and if your m is greater than equal to n, then it follows that x n minus x m is less than epsilon for all m and n greater than equal to. Thus, by Cauchy's criterion, x n is convergent. Now, we define a contractive sequence, contractive sequence. Using the property of a contractive sequence, we can prove some interesting results on convergence of sequences. A sequence xn is said to be a contractive sequence if there exists a constant C such that C is lying between 0 and 1, and we have x n plus 2 minus x n plus 1. The n plus 2th and n plus 1th terms, their difference is less than equal to C into x n plus 1, the n plus 1th term minus the nth term of the sequence for all n in the set of natural numbers. The real number C is called a constant, of the contractive sequence. The following is an interesting theorem. Statement of the theorem is every contractive sequence is a Cauchy sequence, and therefore, because we know that every Cauchy sequence is convergent, therefore is convergent. The proof goes as follows. Let an be a contractive sequence. There exists a C such that C is lying between 0 and 1. We have a n plus 2 minus a n plus 1 less than equal to C a n plus 1 minus a n for all n in the set of natural numbers. Usually we take x n to be the sequence. Here we are taking a n to be the sequence. Otherwise, everything will be same. If we successfully apply this definition, we get the following sequence of inequalities. This is the definition of the contractive sequence. We apply this particular definition and we get a following sequence of inequalities, say a n plus 2 minus a n plus 1 is less than equal to C of a n plus 1 minus a n less than equal to C square a n minus 1 less than equal to C cube a n minus 1 minus a n minus 2 and so forth. Finally, we will get c to the power n a2 minus a1. Now, let m greater than n, and we have c lying between 0 and 1. Using triangular inequality, we get am minus an equal to am minus 1 plus am minus 1 am minus 2 plus am minus 2. I am just adding and subtracting the in between terms of the sequence, and if it goes like this, finally we will get an plus 1 minus an, and that is less than equal to m minus 1, m minus 2, and so on. Finally, it is an plus 1 minus an. Thus, using this result we have obtained here, we will get less than c n minus 1 into 1 minus c to the power m minus n divided by 1 minus c multiplied by modulus of a2 minus a1, and that is less than equal to c n minus 1 by 1 minus c, that is a2 minus a1. Right. Now, c n minus 1 tends to 0 as c is lying between 1 and 0. Thus, for given epsilon greater than 0, there exists n in the set of natural numbers such that c n minus to the power n minus 1 is less than epsilon for all n greater than equal to n. But this implies am minus an is less than epsilon for all m and n greater than equal to n, and therefore an is a Cauchy sequence. Every contractive sequence is a Cauchy sequence. So, as a corollary to this result, we have the following results again. Let xn be a contractive sequence with constant c such that c is lying between 0 and 1, and xn suppose converges to x, then the first assertion is x minus xn is always less than c to the power 1 minus n minus 1 divided by 1 minus c x2 minus x1. This we have already obtained. and the second result is x minus xn is less than c by 1 minus c x2 minus x1. So, these are the two corollaries coming out of this particular result. For the proof of these two corollaries, the first one is, in the proof of the previous result we had, if m greater than n, then xm minus xn is less than c to the power n minus 1 divided by 1 minus c multiplied with x2 minus x1 absolute value. Let m tends to infinity, that is, I am taking only xm. We obtain x minus xn less than equal to c to the power n minus 1 divided by 1 minus c x2 minus x1. This is the first result. For the second result, if m greater than n, we have xm minus xn again less than equal to xm minus xm minus 1 plus and so on. The last term would be x of n plus 1 minus xn. Using induction, we can show that x of n plus k minus x of n plus k minus 1 is less than equal to c to the power k xn minus xn minus 1. It follows that xm minus xn is less than equal to c to the power m minus n plus and finally c square plus c into xn minus xn minus 1. But this is nothing but a GP, and therefore what we have, the sum of this GP is c by 1 minus c, and it is multiplied with x2 minus x1. This completes this module and also this unit. In the next unit, we will be discussing series and their convergences.